In Canvas by tomorrow. Canvas will be available, and on Canvas you will find, number one, you will find notes, you'll find a textbook. We use an algorithms textbook. It was the same book they use at MIT, but we use certain chapters of it. It's online, it won't cost you anything. You just have a PDF. You don't share that book, you just use it here, that's it. And the rest of that stuff is going to be notes that I made up, okay? And then it's going to be lecture. Most of the time you don't have to take a lot of notes, but you can take some small notes because whatever I have here is going to be posted. But sometimes, oftentimes, I like to go off and just, okay, let's talk about this or do something, so I do something on the side. So, we're going to videotape the classes, so if you happen to miss a class, you can try to catch up that way. I strongly advise you to come to class. I can tell you that you will get a better grade if you come to class. I don't know why, it's magic. And it's my experience to know that people do much better if they come to class, if they're following it, if they can ask questions. Okay, I like it when you ask questions. It's a good thing. So we will try to answer your questions as best we can. Anytime, all right? So just don't feel like you have to ask me after class. You can ask me, during class. I have a question. Can you explain this or something? No. So I like questions. I like interacting with you. It's the class. We try to make this class fun because sometimes it can seem very kind of dry subject and maybe not too exciting. Algorithms, why do we have to study it, But it's a very important subject, especially for computer scientists, for people who analyze computing. It's a very important subject for understanding how programs work, the complexity of algorithms, things like that. So we will study a lot of different things here. So the class is called Analysis of Algorithms, right? So everybody has heard, I've used the word algorithm before. Somebody, right? You've heard it. So what does it mean? What is an algorithm? What are we talking about? What is an algorithm?
A blueprint.
A blueprint. Step by step. Okay. So basically, yeah. So an algorithm is basically a formula, a template, a step by step, something that tells you how to go from the beginning of something, how to solve a problem, and if you follow the steps, you should be able to solve the problem and get a solution. What kind of solution? A so-so solution? An average solution? Typically, we want a perfect solution. If we want to sort a set of numbers, and there are 1,000 of them, we don't want 5 or 6 numbers in the wrong place. That means it's not an algorithm because it didn't solve the problem of sorting. Solving the problem means that elements are sorted, right? Finding the smallest element means you find the element which is the smallest so that no element is larger than that one. Okay? Finding the shortest path means that the path between all the different connection points that you can have in a graph, there is no other path which is shorter. That's the shortest path. It's optimal. Okay? So algorithms solve problem optimally. They are guaranteed to work. And they are guaranteed to work in what we call finite time. Now what's finite time?
Measurable.
Measurable, okay? So finite, measurable. Anything else? Anybody else? What is finite time?
Acceptable.
Acceptable? No, it's not. It's not. Acceptable is not part of finite. So, finite time. Is it coming down to my head? Let me know. If it's coming to my head, let me know. I'm pretty quick. I can get out of the way. So what do we mean by finite time?
Limited time.
Limited time. Anybody else? Anticipated time? What does it mean? Finite time.
Measured time.
Those are all nice answers. Can you tell me what I mean by finite time in a different way.
Shortest time?
No.
In a certain period?
That's correct, but I'm looking for something even more clear.
Which has a start and an end.
There will be an end.
Yeah.
When? In finite time. What does that mean? It means it's not going to go on forever, without end. There will be a time. It may be in 3 milliseconds, it may be in 2 minutes, or it may be in 2035 centuries. If it takes 1,000,000 years to solve a particular problem for an algorithm, it's still an algorithm. We're not saying it's not an algorithm. So there are some algorithms which are efficient algorithms, which means they solve reasonable problems in reasonable time. And there are other algorithms which are not reasonable. We call them not feasible. They're algorithms. For example, I'll just give you one example of an algorithm, how it works. It's a very simple idea. How many of you have heard of this problem called the Towers of Hanoi? Have you heard of it? Okay, so a lot of you have heard of it. So, Towers of Hanoi, and some of you who has not heard of it. That's okay. Okay, only 3 guys are admitting it, but you know. All right. So what we have in Towers of Hanoi is we have these things called pegs. They're like sticks. And on top of the sticks, we're going to put these things called discs, rings, widgets. So there's a disk. And so what we have is we have A, B, C are the labels that we're going to use for the no, I forgot the word. For the pegs. Okay, you got to work with me here, okay? So the pegs are A, B, C. Now, the goal of Towers of Hanoi is to move all of the disks, all of the disks from the starting peg A to the final peg C. And then we count the number of steps it takes you to do it. So you have to pretend I'm lifting it because this is just a picture. So you have to use your imagination. So I'm going to lift it, I'm going to slide it here, and in one move, I have moved it from A to C, so that means that the number of steps required was 1 step. All right, so that's pretty easy. So now we're going to advance to having 2 disks. But with 2 disks, I now have to give you a rule. I can only move 1 disk at a time, okay? That's kind of what I did before. I can only move 1 disk at a time, and I can never put a disk which is bigger on top of a disk which is smaller. That's the only rule. So now I cannot simply pick up 2 and say, 1 step again. Then you have 1,000,000. Oh, look. 1 step again. Can't do that. 1 disk at a time, never bigger on top of smaller. So in this case, what I'm going to do, I have to be clever. So basically, it's kind of like a stack because I can only access the top disk. So I can take this one. If I put it here, that's kind of bad because then the other one would have to go only here, but doesn't get the big one onto C. So what I'm going to do is I'm going to move this smaller one onto B, and that allows the biggest one to go onto C in the second move, and the third move moves the smaller one onto here. Okay? So, how many moves did it take? 3. We're not going to go up to 64 today. But we will look at 3. So with 3, I'm going to try to now appeal to your sense of intellect and understanding the concept of what we just did. You understand when we had 2 disks, we were able to move, I understand it's 3 now, so I will erase it for those of you who don't have a good imagination. So we had 2 disks. We were able to, through 3 steps, to move these 2 onto here, using 3 steps, right? Now you understand that I could have just as easily moved these 2 disks onto here in the same 3 steps. And I'll prove it to you by doing this. I will take B and C and interchange them, and then I'll make the same steps, and I'll end up on B, because B is now over here. You see what I'm saying? Oh, algorithms. I see where he's going with that. All right. So now, so therefore, you understand that I can move 2 disks in 3 moves, either onto B or onto C. So if I am having 3 disks, now I'm back to 3 again, and I want to move 3 of them, I'm going to make the following argument. I'm going to say, okay, let's just concentrate not on 3 disks, but 2 disks. And I know that having the lowest one here doesn't cause me any problems, because I will never put, because this is the biggest, so these 2 can be anywhere, and the biggest one is never going to cause any problems, because it's the biggest, and the biggest can always be in the bottom. So just leave it alone, move stuff around. I know that so ignore this one here, so I can take these 2 disks and move them onto here in 3 moves by appealing to our 2-disk problem. Look, just ignore this one, just move these 2, and you know you can do this, right? So you're going to go boom, middle, and little. So I can move these 2 in 3 moves onto here. Once that's done, I can move this one in 1 move onto here, and then to move these 2 onto here, again, it's going to take me how many moves? 3. So total number of moves is going to be 7. So the number of moves with 1, 2, and 3 disks respectively went from 1 to 3 to 7. You can probably figure that to move 4 disks, you got to move 3 disks away, 1 disk, and 3 disks back.
15.
So that's going to be 7 plus 1 plus 7 is 15. So 1, 3, 7, 15, 31, 63, 127, etc., okay. What's he talking about? Okay, what are these numbers? All right, so you get the idea. Now, let's just think about, so that's an algorithm. The algorithm goes like this. To move n disks from A to C, you move n minus 1 disks from A to B, move the big disk from A to C, and move n minus 1 from B to C. You follow the idea? And this algorithm is actually a recursive algorithm. And it's recursive because in order to solve the whole problem of n going from A to C, you solve the problem of n minus 1 going from A to B, 1 from A to C, and n minus 1 again from B to C. And this can be coded recursively. And it's an algorithm. Now, suppose the number of disks is, this number is going to be n. So in this case, n is equal to 3. And then we can make it 4, 5, 6, etc. Blah, blah, blah. So let's say n is equal to 64, which is a lot of disks. But it's not so many disks that you're like, oh wow, I can't count to 64. You can count to 64. There's about 64 people in this room if everybody showed up. Yeah. If you count my bag as a person, then it's almost. So 64 is not such a huge number. And so let's suppose that we run this algorithm because we want to, the output of the algorithm will be the sequence of moves. For example, the sequence of moves of the algorithm will be move the first disks from A to C, from A to B, from C to B, from A to C, from B to A, from B to C, from A to C. You follow that? Of course not. Okay, good. So it's pretty straightforward. So that's the algorithm. So the algorithm can be outputting simply the moves. So let's say I wanted to output this. Now, I was going at the rate of about 1 move if you really want to make me really, good, I can say 1 move per second, which is pretty fast. Now, if I had 10 disks, I don't know if I'd be as fast. But fortunately, computers are pretty fast. They don't lose speed. The calculations come very, very quickly, and they are algorithmically being dictated. So it's not a lot of thinking, not a lot of remembering. They just follow the steps. So suppose I could move the disks much faster than 1 per second. Because 1 per second, this would require how many seconds? 15 seconds. 15 seconds, okay. So if I had 64 disks and I had to move them and I increased my speed of moving them from 1 per second and I made it, for example, I could move 1,000,000 per second. Then I'm really, so I have now a computer which is able to generate a sequence of move at the rate of 1,000,000 per second. And the number of disks is equal to 64. The question is, how long will it take to generate that sequence of moves? I guess we have to have a pretty fast printer too, or screen to display all those moves. It's going to be a lot of moves. And the answer is approximately, to do this at a rate of about 10 to the 6, which is 1,000,000 per second, which is also known as 1,000 per millisecond. It takes approximately 3.6 times 10 to the 61st power centuries. 3 times 10 to the 61st power centuries to make those moves. Centuries. Okay, so even if I said, forgot centuries, 10 to the 61st power years. We don't even know what number this is. 10 to the 61st. 10 to the 6th is what? 1,000,000. What is 10 to the 6th times 10 to the 6th? Times 10 to the 6th. So how many 10 to the 6th would I have to get 10 to the 60th power? So I would have to have 10 of these, right? Times 10, because I got to get 61. So this is 10 times 1,000,000 times 1,000,000 times 1,000,000 times 1,000,000, 60. That's a number we can't really, it's not, that's much bigger than 64, right? We're approaching the number of atoms in our solar system. The bottom line is, at this rate, it would take me this long to make all the moves. So, it's still an algorithm, but if I'm actually wanting to solve the problem, and I'm waiting for the solution to come up, like, okay, when is this going to be done? When is this going to be done? And all of a sudden, I get grayer and grayer. And start getting, all of a sudden I'm dead, and my son is getting older, and his grandson. It's never going to happen in our lifetime or in the lifetime of our children or their children or their children. It's not a feasible algorithm. It's not feasible. I know it's an algorithm. I know it works with finite time because I can tell you exactly when it's going to finish. I just can't wait that long. So algorithms are definitely a set of specific steps to follow to achieve an optimal solution in finite time. But some algorithms, we call them feasible because they can solve reasonable problems in reasonable time. Other algorithms, we call them non-feasible because it takes them longer than we want to basically make good use of these solutions. Okay? So that's very, very important. All right, so what are the tools that we're going to use in this course? This course assumes that you've done a fair amount of programming. Hopefully most of you have taken some serious programming classes and you're good programmers. But I'm not going to give you too many programs in this course. I may give you one, if you're lucky. What we want to do is we want to study the things that you use for programming. Like look at data structures. And look at them more closely than you've ever looked at them. look at algorithms, show that algorithms are correct. We can look at proofs. We can look at proofs is a very important technique of showing that algorithms are correct. Now, some algorithms are obvious. Well, we know they're correct. It's so obvious. But other algorithms, we are not certain that they're in fact correct. So before we implement something, we want to make sure that something is in fact correct. So there are techniques for proving things. These are the same techniques we use for proving anything. Whether it's proving an algorithm to be correct, whether it's proving some kind of theorem to be correct, whether it's showing some geometric postulate to be correct. We use the same techniques. Typically we use direct proofs, we use proofs by contradiction, and we use proofs by induction. Those are basic proving techniques. And every graduate student, and I would say every computer science student in general, every engineering type student, should be familiar with proofs. Because proofs are really logic. You use logic to show that something is true. So we'll study a little bit of that. Okay? We'll also have to be using a lot of quantitative analysis for algorithms. The goal of this course is to put together code and mathematics so that they are inseparable. So if I throw a mathematical formula and I say this is the complexity of an algorithm, you can write an algorithm immediately. Or when you see an algorithm, you should see the math behind it that's driving the complexity. I mean, what I showed you here is, I showed you by demonstration, but really this could be written in code. I could encode this recursive algorithm, and this algorithm would automatically generate some mathematics, which would describe its complexity. Then we should be able to analyze its complexity. And from the analysis, we should be able to say, if you move 1 million disks per second, and you have 64 disks, it will take you approximately this long to solve the problem. I don't know how many centuries that is, but it's a very big number. It's a very big number. It's 1 million to the 10th power times 10 centuries. It's a big number. So it's important to understand that. It's important to understand if somebody gives you a problem and they say, okay, we need the solution by tomorrow. It's important for you as a sophisticated computer scientist and programmer to say, you know something, let me get back to you. And then the next day tell them, I didn't find a solution. I didn't find a solution. That's the bad news. The good news is, I'm not going to find a solution tomorrow. And this guy, who is the crackerjack best programmer in our group, is not going to find it, and neither can 25 of these greatest computer scientists. They can't find a solution either. The reason for that is because this problem that you gave me is in a class of problems that follows certain complexity, for which there's no known efficient solution. So I can't solve it, but neither can all these guys that wrote the books on computer science and algorithms. That's a lot better than working on something for a month saying, I don't know what's wrong with me. So you got to understand what you're going for. You know, are you solving a problem that can't be solved or nobody has solved before? Or do you just need to know a little bit more? So studying algorithms gives you a chance to look at different classes, different types of algorithms, different types of problems, which may have similarly approachable solutions, and they're not all the same. They're different. Sometimes we find algorithms that can solve problems that seemingly don't appear to have feasible solutions. And I'll tell you what I mean by feasible. You already know what I mean by feasible, but I'll reiterate it. Let's say we have an algorithm that we're using to multiply polynomials together. So a polynomial of the third degree has a third degree term, second degree term, first degree term, and a constant. A third degree polynomial has 4 terms. If we multiply a third degree polynomial by another third degree polynomial, how many multiplications do we need to have? 16. So therefore, if we if we multiply two n minus first power polynomials together, how many multiplications do we need? Two n minus 1 power polynomials together multiplied, how many multiplications? Each of the n minus 1 power polynomials has n minus 1, n minus 2, n minus 3, down to the constant. That's a total of how many terms? N terms. Because n minus 1 powers plus a constant. So how many multiplications? N squared. So in terms of complexity, we would say, so now what if I could, so n squared is the complexity of polynomial multiplication as we described it, right? Because what it means is we multiply each of the terms of a polynomial by each of the other terms. So if there are 4 here and 4 here, it's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, right? 16, or in general, n squared. If somebody could find an algorithm that could decrease the number of multiplications in half, does that change the complexity of the polynomial multiplication? Okay, so the short answer is no. Well, it doesn't change the complexity because, again, if we're talking about something like a big O complexity, it's not going to change. Half is not going to change it. It's still going to be in the order of n, because it's going to be n over 2. And half of n is still order of n. Okay, that's interesting. Okay, now can you imagine taking polynomial multiplication of two third-degree polynomials with 4 terms each and creating and having fewer multiplications than 16? Does it seem possible to skip some of them? It doesn't seem logical. And let me ask you another question. So let's say we had a polynomial, and this polynomial was, let's say it had, for the sake of arguments, the degree was 9. So how many terms? 10. And the other polynomial degree is 9 again. So n is going to be 10, n minus 1 is going to be 9. So we're going to need 100 multiplications. 100 multiplications. It's going to be 10 times 10. That doesn't take a long time for a computer to do, right? But what if we had a continuous real-time flow of polynomials that we have to continuously multiply? And we wanted to substantially increase the speed. Or perhaps we had a 1,000-term polynomial multiplied by another 1,000-term polynomial. Then we have 1,000,000 multiplications. What if I told you I can multiply those two polynomials not in 1,000,000 multiplications, but roughly speaking in 10,000 multiplications? Would you believe me? I hope so. But but I hope you have your doubts. Like, seriously? Seriously? How are you going to do that? Okay, so I'm going to try to reduce the number of multiplications. Seriously reduce them. Of course, reducing the complexity of polynomial multiplication can be used in two ways. For giant multiplications, it will speed up the single multiplication tremendously. But for repeated multiplications, it will speed up the rate of multiplying continuously. Get the idea? And so some algorithms are not intuitive. It means we can't really, it's not obvious how we did this, but we can optimize some algorithms in ways that are rather unexpected. And we're going to look at some of those types of algorithms. Okay. We're going to look at algorithms that are greedy. What do you mean by greedy algorithms? When somebody is greedy, what do? They always go for the biggest gain, right? I give you $1 or $3. $3. I give you $10 and $10.50. Okay, they always go. Okay, but now that you got $10.50, I'll give you a cent or 2 cents. 2 cents. But the person that went for $10, now I can give you $100 or $1 million. Oh. So if I wasn't so greedy, I'd have an option to get $1 million, but I was greedy and I got 2 cents. So sometimes being greedy does not give you what? The best solution. It's the short term versus the long term. Sometimes you have to go down to go up. You can't always say just go for the best, go for the best, go for the best. Because when you do that, sometimes you're locked in and now you got all you have is the worst possible left. You're stuck. So greedy algorithms sometimes work, sometimes they don't. You should know. When they work, you should be able to prove this is greedy, but it's optimal. Well, that's good. Because greedy is usually efficient, because it's easy to be greedy. You don't have to consider anything else except what's best for me right now. If you think of a chess, you know the chess game, right? Chess? So if you make a move, if you see the configuration of your opponent and your own configuration, you have a certain number of moves you can make. Always. There's always a certain number of moves you can make. And it's not that large, really. How many people play chess here? Okay, so almost everybody knows the game. So if you play chess, let's say you are making the very first move. How many possible moves can you make? So each pawn, how many pawns do we have? 8 pawns. And each of them can move how many times?
1 or 2.
1 or 2. So that's 16 moves. Then what else can move on the first move? The knight or the horse can move either this way or this way, this way or this. That's 4. So we have so many moves? 20 moves. So that means if I am playing second and you're playing first, I know that for any of the first 20 moves that you can make, I already have a move ready. Right? However, as the game goes on and on and on, the number of moves may be increasing or decreasing. There may be more moves because now more pieces are coming out. Sometimes you lose pieces, so the number can be going down. But there's also lots and lots of moves. But sometimes people make the mistake in chess, and they say, you left your rook out. I'm taking your rook with my queen. And of course, the pawn takes the queen. And that's trying to be greedy. That was greedy. That's the best gain you could have, but unfortunately, it cost you a big loss. So greedy is not always the best. Sometimes we have to consider more. Sometimes we have to say, okay, if I do this, here are your 20 moves, you could do this. Oh, that's not good. Okay. So algorithms are tricky things. They're not exactly the same kind of recipes as when you are making some nice meals. You have to think a little bit, and we will require to do some mathematical analysis. So one of the things that I really like to use, I like to use some basic probability. And if you have not taken a lot of probability or you're a little bit weak on it, you'll see what we need to use. We'll review it in class. And I like to use some basic calculus to look at things like derivatives and simple integrals in order to look at complexity. And they're going to be very, very helpful to us. But everything that I will require you to do math-wise, we will do first. Before we start applying it to the algorithms, we'll be working on the math itself to practice it and to show you how it works, so that you, even if you're not too familiar with it, as long as you've done a little bit of it, you'll be fine. And I'm nothing hard, but you have to pay attention. Yeah, that's all I'm going to tell you. All right. Does anybody have any questions for me for the course? No questions. All right. So that means everything was perfectly understood, perfectly clear. It's always clear in the first lecture. It's the second lecture that gets you. No, just kidding. All right, so everything's good. All right, so I'm going to stop here. I'm not going to start a major lecture today. We will start with the first official lecture on Wednesday. So I'll see everybody at 1:30. All right, have a good day. Enjoy the weather. Yes, now there's a question. Exams? No exams. Everybody gets an A. Wow. Well.